All right. Good deal. Let's see, a couple things. One, somebody asked if I would send, or several people asked if I would send matching problems for the version, for the 6th edition of the textbook compared to the 7th, and I did that, and hopefully that's helpful to you. As I noted in my email, sometimes those problems change a little bit, so I can't tell you they're exactly the same problems, but at least they were the ones that I assigned to students last year, so you can see approximately where those are. I have put a couple of books on reserve in the library. They're not yet available. I think that the library takes a little while to get stuff out there. So when I get the word from the library they're available, they'll be available to you. And I've got a bunch of 6th edition textbooks sitting around as well. So if there's interest in those and you want to take a look at one of those, come see me. I can work with that also. Okay. Not yesterday. Wednesday, Monday, whatever it was. Okay. Monday. I got through talking about just a sort of introduction to biochemistry, and I started talking about solutions and pH, and today I'll spend a fair amount of time talking about pH and buffers. It's important that we all get on the same page with respect to this. Now, somebody asked me a question just before class about, is it true I don't let you use calculators on an exam? And that's true. You don't use calculators on an exam. But you also won't have to come up with a number on the exam. Okay? You're not going to do a logarithm in your head, for example. Okay? It's not something like that. But you will have to know how to use equations and how those equations tell you information. I'll give you some examples of that today. So even though there are problems where you may be actually using a calculator to do them, all the problems that I will assign you, you will not need a calculator to do. Okay? Yes, ma'am?
So we should commit all the equations to memory?
Should you commit all the equations to memory? That's a very good question. In fact, I will give you every equation that you need to know on the exam. Ah. Right? Okay, so you won't need to memorize any equations. You won't have to crunch a number as such. Okay? You will have to know how to use equations and get information from those equations by their very nature. So that's something that you will need to know how to do. The TAs will be helping you in that process, and of course I'm available to help you in that process as well. So don't sweat the calculator component. Okay? All right. Well, usually in my lectures, what I have are a series of figures. I go through and show you various principles and so forth. And this is one place today. Today's an unusual lecture in that I don't really have much in the way of figures I'll be going through and showing you, simply because your book actually, I think, is rather short-sighted. It's one of the few places where the book is not very good in its coverage of the subject, but it's not very good in covering pH and buffers. And so it's important to understand these concepts because, as we shall see, understanding how the pH of a solution affects molecules, we understand better how it affects charges of molecules and ultimately how that affects these molecules that are in proteins. Proteins, we're going to come back to many times, are essential, obviously, for cellular life, but their structure is essential for their function. And one of the things that we will see when we start talking about proteins, and I'll actually, you know, when they redesigned this room, I was told that was going to go away. Space aliens are still here, I guess. Okay. When the proteins get different charges, they adopt different shapes. And so we change the ability of a protein to function as we change the pH of a solution. So what I'm going to do today, oh, don't do that. Okay. What I'm going to go through today is talking about pH and buffers. Okay, so it's very important to understand that. All right. Well, last time I introduced the topic, I said pH, of course, we know is the negative log of the hydrogen ion concentration, and pOH was the negative log of the hydroxide ion concentration. Freshman chemistry. Okay. pH plus pOH is equal to 14. Okay. And by the way, I think you should be able to add 14 and subtract 14 without a calculator. So there are, I can't tell you, you won't have to do simple math, but you won't have to do any crunching. Another concept I want to introduce here, I talked last time a little bit about the fact that there's a difference between strong acids and weak acids. And we will be mostly concerned in this course with weak acids. That is, acids that do not completely dissociate in water, okay, at a certain pH. All right? Now, a prime example of that, acetic acid, as I said, acetic acid ionizes to a very limited extent. If I put it into water, I might get 1 molecule in 1,000 that are ionizing. Okay? I put HCl in water, and I get every one of them that ionizes, meaning they come apart. All right? So there is a fundamental difference between weak acids and strong acids. If I know how much HCl I start with, I know how many protons there are there. I don't necessarily know that if I have acetic acid. The number of protons that I will have free in a solution where there's acetic acid will depend on the pH of that solution. Okay? The ionization of acetic acid varies with pH. That's number one. Ionization of a weak acid varies with pH. Okay? Now, we'll see that mathematically, and I hope that you think in mathematical terms instead of memorization terms. I can tell you, for example, if the pH is high, we're going to have more ionization than if we have the pH being low. Okay? When I say ionize with respect to a weak acid, I'm talking about a proton coming off. That's what ionizing is all about. For HAC, I can write HAC goes to H plus AC minus. Okay? That is an ionization right there. I'm making 2 ions. Okay? Now, this equation you're going to see over and over and over because it's important that we understand what's happening in that ionization. All right? Well, how do we determine, are all weak acids the same? Well, they're not all the same. In fact, we see enormous variety in the strength of weak acids. If I were to define strength of weak acid to you, I would say at a given pH, a relatively strong weak acid will ionize more than a relatively weak acid. Now we get strong weak acids and weak acids, right? Nothing like confusing the picture on the second day of class. Okay? That's important. Okay? Now, how do we compare those? Well, we compare those where there's a measure of the strength of an acid. It's a constant known as Ka. We won't even concern ourselves with that. We're going to be concerned with the negative log of Ka, which is known as the pKa. So just like pH is the negative log of the hydrogen ion concentration, and pOH is the negative log of the hydroxide ion concentration, pKa is the negative log of the Ka. We probably won't talk about Ka again after today. We will talk a lot about pKa. So what is pKa? pKa is a measure of the strength of an acid. A strong acid like HCl has no pKa. It completely comes apart. Okay? A weak acid like acetic acid has a pKa of 4.76. Okay? What does that mean? Okay, I'll tell you what that means in a second. But I'm going to compare the pKa of acetic acid with that of formic acid. Okay? Formic acid is also a weak acid, but its pKa is 3.75. And no, you don't need to memorize these numbers. You'll be given them if you need them. Okay? If I compare acetic acid to formic acid has a pKa of 3.75, acetic acid has a pKa of 4.76. Formic acid is stronger of a weak acid than acetic acid is. Okay? Are we clear on that? So if I'm comparing the two, I compare their two pKa's. The one that has the lower pKa is the stronger acid. Now we could derive all the math that's necessary to do that, but we really don't need to do that in this class. Okay? Simple concepts about what Ka is, or what pKa is, I'm sorry. Okay. I've said HCl, strong acid, doesn't have a pKa. Okay? We don't even consider it because it just completely comes apart. We can't mess with that. All right. So the lower the pKa, the stronger the acid. All right? I don't know why it does that. Do you have your phone in your pocket? I do have my phone in my pocket, but I don't think that should be doing that. Should I mess with it?
Yeah, that'll give feedback across it.
Put it on airplane mode. I've tried this before, but it doesn't seem to make it go away.
You made it work here?
I'll just jump. Okay. Now, I apologize for that noise, but I think it's something this room is haunted or something. It doesn't, it's stuck there. All right. let's think about that weak acid. Let's think about acetic acid for a moment, and let's think about what happens with it in solution. I said if I just dump it into water, okay, a pretty small percentage of that HAC becomes H plus and AC minus. When I'm concerned about pH, the only thing I'm concerned about is the H plus, not the AC minus, right? If I have it sitting there and let's say I put 1 million molecules of acetic acid into that aqueous solution of water, and 1,000 of those protons come off. I'm going to have 1,000 protons come off from there. I'm going to have 1,000 AC minuses, right? And I'm going to have 999,000 HACs left behind, right? Everybody with me? Let's say I add some sodium hydroxide to that solution. Sodium hydroxide, of course, is a strong base. And like a strong acid, a strong base completely dissociates in water. So if I put 1 million molecules of NaOH into a solution of water, I get 1 million molecules of Na plus and 1 million molecules of OH minus, completely dissociate. So a strong acid is equivalent to a strong base in terms of its strength. They completely come apart. Let's imagine, if you will, that I put 1,000 molecules, or let's make it fun. Let's put 449,000 molecules of OH minus into that solution. Okay? What's going to happen in that solution? I'm going to have an excess of OH minus, right? Is the pH going to go way up? It's going to go up. But it's not going to go up as much as you might think. Why not? Go ahead.
Buffers have a limit.
Well, you're getting ahead of me in terms of definition of what a buffer is. But yes, buffers. There are buffers. This is acting as a buffer. But I don't even want to use that term yet. Why doesn't the pH just go through the roof?
Acetic acid dissociates.
Acetic acid can dissociate. So I had 999,000 molecules of that HAC that was sitting there, right? Some of those could give up protons, right? And what's OH going to do when it hits a proton? Well, it's going to hit with a proton and make water, thereby neutralizing it, right? So if I had 1,000 molecules of H plus and I had 1,000 molecules of AC minus, and I add 449,000 molecules, what am I picking 449? 499,000 molecules of NaOH. 499,000 molecules of that HAC is going to give up protons. It's going to give up protons. And at that point, I'm going to have 500,000 molecules of AC minus, and I'm going to have 500,000 molecules of HAC. Right? 1,000 plus 499,000. Right? With me? You can say yes, Kevin. No, you can't, obviously. Okay? All right. At that point, I have 500,000 molecules of HAC, I have 500,000 molecules of AC minus, and I've got a higher pH. That higher pH turns out to have an important name. When I have equal numbers of AC minus and HAC, I've reached the pKa. pH equals pKa when salt equals acid. With me? pH equals pKa when salt equals acid. So pKa is simply a pH. It's a special pH. It's the pH at which salt equals acid. Now, I told you that acetic acid had a pH of 4.76, right? That tells you something. It tells you that pKa, I said pH, has a pKa of 4.76. That tells you that pKa is a constant. It's a constant for a given acid. Whenever I have acetic acid, it will always be 4.76. It will never change. I can change the protons, I can change the hydroxide, but the pKa will be a constant. The pH will change, but the pKa won't. All right? Well, it turns out that there's an equation that relates these things that I'm telling you just conceptually at the moment. Okay? The equation is an equation you're going to hear a lot about. It's called the Henderson-Hasselbalch equation. And the Henderson-Hasselbalch equation states that, here we go, pH equals pKa plus log of AC minus over HAC. More commonly, we will say that pH equals pKa plus log the concentration of salt divided by the concentration of acid. I call the thing that has lost the proton the salt. And I think you'll find it much easier to understand if you call it the salt instead of the base. Okay? So pH equals pKa plus log of salt over acid. Acid is the thing that has the proton. Acid is not the proton. The acid is the thing that has the proton. So the difference between a salt and an acid is a single proton. There it is right there. Okay? Now, everybody understand the terms I'm talking about, right? Salt, acid, Henderson-Hasselbalch equation. We're going to use the equation in just a second. How do I make something into a salt? I take protons off of an acid, right? I can convert acid into salt by taking protons off, and in the example I just gave you, how did I take protons off of the acid? I added a strong base. Okay? If I wanted to put protons onto that salt, how do you suppose I would do it? I would add a strong acid. Okay? How would I put protons on? Well, if I start dumping protons into this reaction right here, what's going to happen to this equation on the basis of the principle of Lavoisier? It's going to move it to the left, which means I'm going to make this and I'm going to lose this. Right? You've already saw how it went to the right. When I start taking protons away, the solution starts trying to make them up. Starts trying to replace them. It starts making more AC minus. There's a one-to-one relationship. For every molecule of strong base I added, I lost one of these and I made one of these. The same holds true if I go the other way. If I go the other way and I add protons to this solution, if I add 500 molecules of HCl, I'm going to lose 500 of these. I'm going to make 500 of these. Understanding that is the most common thing that students screw up on buffer problems. The single most common thing they screw up on. There's a one-to-one relationship between adding and subtracting acids and bases. That's all there is to it. It's a very simple concept. Okay? Now, let's go back to our equation. Our equation said that pH equals pKa plus the log, the concentration of the salt, divided by the concentration of the acid. Right? In the example I gave you, we had 500,000 molecules of salt and we had 500,000 molecules of acid. Let's plug in to that equation. They're in the same volume, so the volume cancels out. We don't have to worry about concentration. We can actually use numbers. Okay? pH equals pKa plus the log of 500,000 over 500,000, and you have a hand up.
Is that a dash or a negative?
Where?
The negative.
This?
Dash.
That's a dash. Yeah. That's not a negative. That's a dash. That's a good question. I didn't even notice it was a dash there. Yes. Maybe I'll remove that dash so you don't get confused. That's a dash. It's not a negative pH. That's just a dash. pH equals pKa plus log of salt over acid. Now, let's think about that. Let's plug in our terms. I want to find the pH of the solution I've just defined for you. I've made a solution of acetic acid. I have a pKa of 4.76 because that's a constant for acetic acid. And I've got 500,000 molecules of AC minus and 500,000 molecules of HAC. What's the pH? 4.76. You can tell it by either the fact that I just told you when the two are equal, that makes sense, but you can also tell it, more importantly, from the equation. The log of 500,000 over 500,000 is the same as the log of 1, and the log of 1 is equal to 0. Yes, you have to know that, but I'll even put that on the exam. Okay? That's cool. Okay? That's cool. So now I see mathematically why the pKa is the pH at which the salt equals the acid, because when the salt equals the acid, this log term becomes 0, and pH equals pKa. Questions? I'm kind of going through this kind of blah. Am I that clear? I know I'm not. Am I that fearsome? I probably am. Yeah? Oh, is there a question? I'm sorry. Yeah. If I want to increase the amount of salt, okay, I would have to pull protons off of the acid using a strong base. Okay? Important concept, and thank you for asking the question. If I want to make acid from salt, I've got to put protons in, which means I've got to add a strong acid. Yes?
So to make acid, you have to use an acid.
In order to make acid in this system, I have to use protons from a strong acid. That's correct. Okay? Good. So I guess if there's no questions, then you guys are ready for a pop quiz. That means you've already understood it, right? Or are there questions? Because I'll find out real quickly if you understood it or not. I guess if there's no questions, then you must understand it, so therefore the pop quiz is relevant, right? Nobody has a question?
I have a question.
Okay, good.
What's the NA
You just saved the whole class right there. They should thank you.
What's the NA doing why it dissociates from the OH in a strong base?
So I add NaOH, what's happening to the Na? Nothing. Just sits there.
Just hangs?
Just sits there.
And that goes the same with your strong acid. It's just going to
The Cl is just going to sit there.
chill out.
And if you keep adding strong acid and strong base and strong acid and strong base, you start making NaCl and NaCl, and you got a very salty solution, and that's all that happens. Other good questions. So, you're saved from a pop quiz. How about that? I won't be so nice next time. All right. Now, what we're starting to understand, or what I hope to introduce next, is the concept of what is something called a buffer. Okay? You used the term up here what a buffer was. We need to talk about what a buffer is. So I'm going to define a buffer for you, and then we're going to go through some examples. All right? A buffer. Buffers are absolutely essential. You'll see why the further we go along. All right? Definition of a buffer. A buffer is a system that resists change in pH. It resists them. It doesn't prevent them. It resists them. Okay? In the example I gave you, we dumped a whole bunch of OH in there, but the pH didn't go up very much. And I'll show you a graph of that in a bit. Okay? The system is acting like a buffer. It's preventing the pH from going up as much as it would if the buffer weren't there. There's a couple of problems that I've assigned in your book that will illustrate to you what a buffer is and how a buffer works. And you'll compare those. Actually, it's not in the book. It's actually one of the ones I made up for you on the system, okay? Where there's the ones that Kevin made up on the side. All right? If you click on those, you'll see a couple of them that will illustrate to you how a system that has a buffer differs from a system that doesn't have a buffer if you add the same amount of protons. And you'll see there's a very big difference between the two. Now, so I've defined a buffer for you. A buffer is a system that resists change in pH. Yes, ma'am?
Does it work the same whether the buffer starts in a system or whether you add the buffer later?
Does it matter if you add the buffer first or you add the other stuff later? It turns out it technically doesn't, no. Okay? Good question. Yes, sir?
Approximately what's the effective range pH-wise of the average buffer?
Oh, this is a very good question also, and thank you for asking that very much. What's the range of a buffer? Okay. Is a buffer an infinite thing? Can a buffer resist pH changes forever? No. Okay. Buffers have what we call capacity. We'll see some examples. In fact, one of the problems in your book actually illustrates capacity to you, and it's going to confuse you when you first do it, because it's not going to make any sense. And that should be a clue that something isn't what you think it is. But to answer your question, what's the range of effectiveness of a buffer? It's mostly a definition thing, but effectively most buffers are good within 1 pH unit above or below their pKa. So for acetic acid, the effective buffering range, that is where it's best at resisting changes in pH, is from about 3.76 up to about 5.76. 1 pH unit of its pKa, either way. Okay? And I haven't given you an example of how a buffer works yet, so I'm going to do that in a second. But other questions just in general about buffers? Okay. All right. I keep you look up also. Make sure I see people up there. Yes?
So, will a buffer work outside of its effective range?
Will a buffer work outside of its effective range? Yes. I mean, will a buffer participate in accepting or donating protons outside that range? Yes. But its effect on controlling the pH will be minimized. So we won't see as strong of a protective effect if we get outside of that range. Good question. Okay? All right. So how does the buffer work? Well, let's think back to this buffer this system that I just described to you. I've got a solution that has 500,000 molecules of AC minus, and it has 500,000 molecules of HAC. Okay? Equal numbers of salt and acid. Let's imagine that I add 10,000 protons to that system. You can do the math pretty quickly and say, well, you're going to have 501,000 molecules of HAC because we're making HAC. I'm going to have 499,000 molecules of AC minus because I lost AC minus, right? How much would the pH change? Well, it turns out it's not going to change very much. Okay? How would I know? I'd plug it into the Henderson-Hasselbalch equation, and what I would see is that I would have pH equals 4.76 plus the log of 499,000 divided by 501,000, right? That's very close to 1. It means that log term is very close to 0, right? The buffer is protecting us. Where there's excess protons, the buffer grabs them. Where there's excess OH, the buffer makes protons. Okay? Very, very important concept.
The buffer, in that example you just gave, what did you give us what your buffer was, or did you just say you added this much buffer?
So acetic acid is the buffer system here.
Oh.
Okay? So thank you for asking that also. All right? Weak acid systems make great buffers. Anything that has a pKa makes a great buffer in a certain range. Okay? Anything that has a pKa makes a great buffer in a certain range. Now, in this example I just gave you, we don't see the pH change very much. It's a very minuscule change that happens, and that logarithm of it actually makes it an even smaller change. If I did this, I would ask you, a reasonable question for me to ask you on an exam would be, is the pH higher than the pKa, or is the pH lower than the pKa? I don't have a calculator. Okay? You don't have to have a calculator to answer that question. How would you answer that question? It's lower. Why would you say it's lower?
It's been acidified and the lower pH.
Okay, so he says it's been acidified, and it's true, it has done that. But one of the places where students confuse themselves is with acidification. Okay? I want you thinking mathematically. Mathematically, why is the pH lower than the pKa? And it is lower than the pKa. You're right. You're taking the log of a number that's less than 1. Exactly. 499,000 divided by 501,000 is a number less than 1. Just like 499 over 501 is less than 1. The logarithm of a number less than 1 is a negative number. So if I have 4.76 plus a negative number, I have to have the pH lower than 4.76. Right? What if it were higher? What would I have to do to add to the solution to make it be, for example, 501,000 molecules of AC minus and 499,000 molecules of HAC? What would I have to add to make that happen? I wouldn't add salt. Okay? I would have to add HCl. I could add salt, but not based on what I just told you. I didn't change the total amount. I said 499 and 501, right? If I add salt, I'm going to have 501 and 501, right? I'm going to have a different total amount. When I add a strong acid, I convert salt into acid, and my total stays the same, 1 million molecules. So I add a strong base to that to make that happen, to pull those protons off, to switch the HAC into AC minus. Everybody clear on that? Okay. If I told you I had a solution that had a pH of 4.3 and the system had a pKa of 4.9, more salt or more acid? pH 4.3, pKa 4.9. What does that say about the log term? What does the log term have to be? It has to be negative. To have a negative log term, what do I have to have? I have to have more acid, right? Has to be less than 1, which means I have to have more. And by the way, HAC only holds for acetic acid, so to make it general, we call it A minus and HA. Okay? So I have to have more A minus than I have HA. Okay? Now, these are the kinds of things that you can work completely without a calculator. You can manipulate that log term in your head. Bang, you got it right there. You don't have to have a calculator. It's important for students to learn how to work problems, okay, to understand the math of what's there, not to see the confusion of the numbers. That's why I don't want you using a calculator. I want you to think about these things. I want you to understand them at a real level and not at a da-da-da-da-da-da level. Because if those numbers that you da-da-da-da-da in there don't have meaning, then you'll get garbage out as well. You have to put the right stuff in. And so what I'm trying to get you to do is to understand how to put that right stuff in. On my exam, all you will have to do is get a solution to the point where it would go into a calculator. If you get down, this is the logarithm of 3. If the logarithm of 3 is the answer, that's it. You don't have to calculate that. Okay? Make sense? Okay. Let's see. Other questions about it? I'm going to show you a couple of examples after, if you don't have any questions. Nobody? Okay. All right. So let's see a buffer in action, right? Yes?
This morning in recitation, our TA told us to always assume that the concentration of AC minus plus HAC is 0.1 molar.
Not for a buffer, no. A buffer can have any concentration.
Okay.
That was the concentration in that specific problem.
Okay. Okay.
Okay, so just don't always assume.
No. So buffers can have any concentration. And that's important because buffers, I can make a buffer be as concentrated as I want to. So if I say the word buffer, here's something I want you guys to pop into your heads. All right? When I say the word buffer, I want you to think of two terms I've been using over and over. All right? Salt and acid. That should immediately pop those two up in your head. When I say buffer, if I told you I have a buffer that is 0.1 molar, the first thing that should pop into your head is salt plus acid equals 0.1 molar. Because when I have a buffer, I have to have both of those. I have to have salt and I have to have acid. Okay? Now, the actual amounts of those you may have to calculate, all right? But when I say buffer, salt plus acid equals the total amount of buffer. All right? In this case, it was 0.1, but it could be a variety. It could be anything I make up. Yes, Connie?
So just to clarify, did you say if a buffer is 0.1, then salt plus acid equals 0.1?
If I say a buffer is 0.1, say 0.1 moles of buffer, if I said I had 0.1 moles of buffer, then salt plus acid would equal 0.1 moles. That's correct. Okay? Make sense? Okay. Now, the concentration of a buffer is important. Let's think about a 0.1 molar buffer. Let's say I've got a 0.1 molar buffer of acetic acid, my favorite acid, right? And it's at its pKa value. Its pH is at its pKa value. What does that tell me about the concentrations of salt and acid in that? They're equal, and they're equal to what? 0.05 each, right? Half the total. What if I add, let's say, 0.1 molar HCl to that in equal volume? What's going to happen to that buffer? Based on what I've just told you, what are you going to see happen? I add HCl, I'm going to lose salt, right? I'm going to make acid. How much salt can I lose? 0.05. But I've just added twice that amount of HCl. Uh-oh. When I start doing my subtracting, I discover I have a negative amount of AC minus. Can I have a negative amount of AC minus? No, something's wrong here, right? Something's wrong, Houston. Okay?
How much?
What I've done, I added 0.1 molar. Okay? What I've done is I've just given you an example where I have exceeded the capacity of the buffer. Buffers have limited capacities. All right? They're not infinite. So one of the reasons we change the concentration of a buffer, okay, is so we can change its capacity. All right? Capacity is important. All right, so you'll see one of the problems in the book will actually exceed the capacity of a buffer. When you get to it, I think you'll figure out what it is. Okay? Yes?
So regardless of the concentration of the buffer, the capacity won't change for a specific acid.
I'm not sure I understand the question.
So let's say you have 500,000, or you have 0.1 molar versus 0.05 molar.
Uh-huh.
The capacity is going to stay the same.
The capacity is defined by the salt and acid that's there. So if I add more than that of strong acid or strong base, I'm going to exceed its capacity. Okay? Connie?
So it's not dependent on the concentration at all?
It is dependent on the concentration, absolutely.
Oh, well, because you say that it's usually within 1 pH unit of
Yep.
pKa.
Yep.
Would it be have like a really concentrated weak acid buffer? Would it?
Well, that's a mathematical question that you're asking me to define non-mathematically. So come see me, I'll show you mathematically what we're talking about, okay? But 1 pH unit, you're not exceeding capacity. Okay? But 1 pH unit is going to define how much I can add to it to get to that 1 pH unit, right? So I'm limited by that.
Okay.
All right. Okay. So buffers have capacity. I can't exceed those capacities because if I do, the pH is going to go boing because I no longer have a buffer. The buffer was providing me that protection against massive change in pH. When I exceed the buffering capacity, I don't have a buffer anymore. It's gone. pH is going to go sproing. Okay?
So
Yes, sir.
Could it be generalized that the capacity is going to be defined both by concentration and volume combined of the buffer?
So the capacity of a buffer is, so the question that you're asking is, if I know the number of moles total of buffer, that defines ultimately the capacity, because concentration times volume gives me that, and the answer is yes. Okay? Okay. Now, I know you're going to have some struggles with this, and I understand that. Please come see me. Please come see the TAs. Work through the problems, okay? I can guarantee you that they will be help in getting an understanding of this bigger picture, okay? It's important to get that bigger picture, and keep an eye on the time. Okay. Okay. I promised to show you a buffer plot, and this very high-quality graphic was drawn by yours truly. This was for you guys in freshman chemistry did a titration curve, right? Did you like titration curves in freshman chemistry? You did? Okay, good. Most people don't like them, all right? So this shows the relationship between the pH of a solution and the amount of OH I added. In this case, I started with a solution that had essentially all acid to start with. How do I know that? Well, I had a low pH, and right down here at a low pH, how would I know if a low pH I would have most of the acid to start with? How would I determine that? Nobody? If I said extra credit, then everybody would jump, right? I didn't say I was giving extra credit. I just said if I said extra credit, okay? The question is, how would I know down here that I've got most things in the acid form? What's that? But I'm not talking about protons. Protons are not acid. I'm talking about HA. How would I know I'd have most everything in the HA form? You have a friend. What is the friend? The friend is Henderson-Hasselbalch equation. All right? If the pH is low, below the pKa, what happens to that ratio? More salt, more acid. More acid, right? Bingo! Henderson-Hasselbalch tells me, and it tells me very quickly. The answers to virtually every question I'm going to ask you will be rooted in that equation. They're going to be rooted there. Okay? You want to get familiar with that equation. Now, let's see what happens with the solution. I start out with this solution. It's got the protons on. I start adding sodium hydroxide. What happens to the pH? The pH rises. It rises relatively rapidly at first. Why does it rise relatively rapidly at first? It's outside the buffering region. The buffering region being plus or minus 1. In this case, the pKa I've got for this is about 2.5. Okay? So I'm below 2.5. It rises relatively rapidly, and then it starts to level off. And it's leveling off because it's acting as a buffer. It's resisting the change. I'm adding a lot more hydroxide, but the pH is not going up very much. Once I start getting away from that region, by more than 1 unit, all of a sudden I see the pH going boing. Every buffer plot is going to look like this. Okay? This is a visual image of what a buffer is doing. It's resisting a change in pH at a certain range. The maximum resistance is right here, where pH equals pKa, and that's another important concept. Not only is pKa the pH at which a buffer has equal salt and acid, it's also the place where there's maximum resistance to change in pH. We have maximum buffering capacity. There's a question here? Yeah.
Molecularly, why does it do that? Why doesn't it just continue on? The more you add, the more it gets dissociated.
It is associating.
I know, but why does it plateau? Why wouldn't it just continue with just the breaking of the bonds? I don't know. Why is it pause?
Why does it go up and then flatten?
Yeah.
Okay. Well, two reasons. All right. One, plug it in mathematically. Plug in a whole bunch of different values of salt and acid in that ratio, and you'll see that mathematically that's exactly what it does. So mathematically, that's the answer to your question.
I'm talking more molecularly, like bond-wise. You know what I mean?
Well, you're talking about ionization,
Yes.
right? Okay. So ionization is happening because the absence of a presence of protons. This Lavoisier's equation with the HAC going to H plus and AC minus. We put pressure on that equation one way or the other. That favors the ionization. Okay? Yeah, question? What did I say? Le Chatelier's principle. God, I do that all the time. It is Le Chatelier's principle. Sorry. Yeah. Lavoisier was the practical inventor of chemistry, not Le Chatelier. But yes, thank you. It is Le Chatelier's principle.
Are there ever systems where multiple buffers that have overlapping ranges of effect are used, where you could have one at, say, 1.5,
Yeah.
2.5, 3.5?
Yeah. So can you have multiple buffers in there? The answer is you can. We're going to do buffers one at a time. So I figured you've got enough to think about. But yes, you can. And multiple buffers do complicate the picture a lot. Yeah. We'll see starting on Friday, I'll be talking about amino acids. And amino acids have multiple buffering regions. And so you'll see a flattening, a flattening, a flattening that can happen. And so that is a simple example of what you're talking about. Yeah. Okay? Okay, now I promised you guys, any questions about this? We've gotten through a good number of things. I want you, the most important message I want you to take across, get across from this, is that the ionization is going to be related to pH and its relationship to the pKa. pH, the ionization of a substance is related to the pH of the solution it's in and its pKa value. The more the pH is above the pKa, the more the protons will be gone. The more it's below there, the more the protons will be on. And you don't need to memorize that. Henderson-Hasselbalch tells you that. But I'm saying in words to you what Henderson-Hasselbalch is telling you. Okay? That's a lot of stuff. Why don't we finish with some fun? I thought we might celebrate Henderson-Hasselbalch with a song to the tune of My Country 'Tis of Thee. I've never sung this in front of a class before, so let's do this. Henderson-Hasselbalch, you put my brain in shock. Oh, woe is me. The pKas can make me lie in bed awake. They really give me bad headaches. Oh, hear my plea. Salt-acid ratios help keep the pH froze by buffering. They show tenacity, complete audacity, if used within capacity to maintain things. I know when H's fly, a buffer will defy them actively. These protons cannot waltz when they get bound to salts. When this is changed in pH halts, all praise to thee. Thus now that I've addressed this topic for the test, I've got know-how. The pH I can say equals the pKa in sum with log of S or A. I know it now. Okay, good place to stop. Thank you.